Okay, so wave nature, what de Broglie said is, so far, based on all the research that Planck did, that Einstein did, what was known about light, like all the phenomenon, interference, diffraction, and also like the photoelectric effect, it has been accepted that, okay, light has particle nature as well as wave nature. So light can exist as photons, pinpoint particles, or it can, travel as electromagnetic waves. Okay, so de Broglie had this idea that, okay, so if light can have dual nature, then why not matter? He was just, like philosophizing. If light exists as dual nature, why not matter? And then it was not a random idea. He was like, in nature, everything should be symmetrical. And then he did the mathematics behind it also. Okay, so he wrote his paper, he put down his whole concept and all of that. So essentially what de Broglie says is that, so like matter, everybody knows that matter is made up of particles, right? Atoms. So what if these particles also had a wave nature associated with them? So this is what the videos that I shared with you is all about. The second video, when it comes like that, talks about Heisenberg's uncertainty principle, but that uncertainty principle originates from the concept of, the dual nature of matter. So like matter being a particle and a wave. Okay. And the expression that de Broglie said, okay, if matter should have wave nature associated with it, then obviously wavelength, frequency, all of this should also be there, right? So the expression that de Broglie gave to figure out what is the wavelength of matter is that lambda is equal to h by mv, or h by p. So where lambda is the wavelength of the matter wave.
Ma'am, in this I just had one doubt. So why is this lambda or the wavelength called as the de Broglie's wavelength? I mean, that's just the same wavelength, right?
Yeah, de Broglie wavelength is basically a wavelength of matter.
But this is like applicable for matter and like not normal waves.
Yes.
So that's why, since he invented the term.
Correct, because it's his concept. Yeah. And h is your regular Planck's constant, 6.626, that particular value. And p is the momentum of that particular particle. So momentum matlab mass into velocity. It's traveling with some velocity. Yeah. Yeah. So the whole thing, like we did all these calculations in the previous class. All the matter in the universe has a wave nature, just that it is not perceived for macro objects. Macro meaning large objects, like anything that can be perceived by human eyes, including like sand grains and things like that. Okay, so macro objects, it is practically negligible. Like imagine if the wavelength was in the order of 0.0000, and if you had like almost like 36 zeros and then some value almost equal to zero itself. That is the reason you don't perceive macro objects as matter waves. Practically negligible. But when it comes to subatomic particles, when it comes to quantum particles, like electron, proton, alpha particles, like really, really tiny particles, there it gets significant because the wavelength of these objects is in the order of 10 raised to the power minus 10, 10 raised to the power minus 9, which is basically same as the wavelength of light. And you can perceive light. So that is the reason for quantum particles, like de Broglie's matter wave concept is really, really important. Okay. Now that okay, Ritu, like this is what is the whole point or concept of like de Broglie's matter wave. Just like light, Matter also has wave nature to it, and the wavelength of that particular thing is given by this formula. So all your problems questions will be based on this only. The significance is that for macro objects, it doesn't really make a difference because wavelength is negligible. But for micro objects, it is very, very, like for subatomic quantum particles, it is extremely important because now it is established that electron can exist as a particle and also a wave. Okay. Which means that if electron was a wave is basically transmission of a disturbance, right? Remember our water wave, this thing, like if you have a pond in which you drop a stone and then there's like waves created all around the pond, can you pinpoint the exact position of the wave? You cannot pinpoint the position of the wave because the wave itself is like the definition of a wave itself is the transmission of the disturbance. Wave is defined by its movement, which means that if electron exists as a wave around the nucleus, we cannot pinpoint exactly where that electron wave is. We can just give a rough idea of, okay, it is somewhere around nucleus in this particular region. Maximum probability is that it exists at a distance of, I don't know, 52 picometers from the nucleus, but you can't exactly say that, oh, this is the electron right here and it is traveling in clockwise. Like you can't establish that. Okay? And because of the wave nature of electron, this gives rise to, because now you can't precisely point out the position of the electron as such, that gives rise to Heisenberg's uncertainty principle. So that's what Heisenberg was getting at. So Heisenberg's uncertainty principle, so the uncertainty part comes from the fact that you can't be certain, you can't exactly pinpoint the position and the momentum of an electron simultaneously. Yeah, because the momentum or the velocity comes from the wave nature of the electron and the position comes from the particle nature of the electron. So if like, you know, like you can pinpoint a position of a particle, you can't pinpoint position of a wave. And at the same time, if the electron has momentum of it, then, you know, like the wave nature gets more significant and then, you know, you can't pinpoint the position of it. So yeah, that's what Heisenberg said, that like you can't pinpoint the position and the momentum simultaneously. Either you get the position in like to a better degree of accuracy, in which case you don't know what the momentum is of the electron, or you get its momentum, in that case you don't know what the position is going to be with that much accuracy. Yeah, someone.
So yeah, Heisenberg's uncertainty principle, it only works for like particles already in motion, right?
Yes, absolutely, because you need the momentum aspect of it. And secondly, again, just like how the wave nature is significant for subatomic particles, Heisenberg's uncertainty principle also applies to subatomic particles. Because for normal particles, like the wave nature is so low that you can point out the position and, you know, the momentum of large objects quite easily. So this is applicable only to the particles that show dual nature. Mainly applicable to electron. Okay. So this tripped up entire Bohr's model, because Bohr's model was like, he built his own, like the first postulate of Bohr's model was that electrons revolve around the nucleus in circular orbits. Now orbits are nothing but pathway of the electrons. So if you can't figure out the momentum and the position simultaneously, how can you tell the pathway of, you know, how an electron is going? right? So that is where like the Bohr's model has been slipped up. But Bohr had his own merits. Like he said that angular momentum is quantized, and he gave the radius of hydrogen atom to a degree of accuracy. Like he had his own merits. Just that because he considered the particle nature of electron, like this particular part of it is not correct. So if electron was a wave and you can't figure out where exactly it is, this gives the concept of the electron cloud. Okay, so you can't really say for sure where exactly the electron is or how it is spinning, but you can figure out that, okay, there is a region in space where the probability of finding an electron is pretty high. So if you take all of these positions together and you plot them in a 3D space, what you get is basically the probability density distribution of the electron, which people also call the electron cloud. Okay. So this kind of representation basically tells you that there is the darker areas are, you have more probability of finding an electron. The lighter areas are, you have less probability of finding an electron, but it can be here, or it can be here, or it can be here, or it can be here. It can be anywhere around the nucleus in this particular shape.
Excuse me, ma'am.
Yeah.
So even though like the lighter parts have a lesser probability, the electron can still be found there, right?
Yeah, just that the probability is less. Okay. So this is basically the crux of the quantum mechanical model of the electron, which is given by Schrodinger's wave equation. Okay. So Schrodinger's wave equation, it gives it's a mathematical representation of where all you can find an electron around the nucleus. So that's what it is. So again, that's also restricted, right? Like it's not like, oh, Schrodinger gave this equation and then it's not random basically. Like that also follows a pattern, like a definite pattern, because obviously the energies and the attraction, repulsion, all of it has to be balanced and satisfied. Like it needs to follow a certain order. So what that order is characterized by the quantum numbers. The quantum numbers, you have n, l, and n. Here. Again, yeah.
Ma'am, so I had a doubt in if the subatomic particle was at stationary. So as the velocity will be 0, we still wouldn't be able to find the location of the particle, right? Even if the speed was 0.
I didn't get you. Why will
So
the speed be 0?
no, it's so the question was if this object is at stationary, will the Heisenberg's uncertainty will it work or not? So so as I said, if the particle was at stationary, so even though it's at stationary, we cannot find the location or the position of the subatomic particle, right?
No, you can't. Yes.
Uh, so since it's at rest, but we cannot find out, how can we not find out if it's at rest? I would have agreed if it was on motion, but if it was in rest, how can we not find out the position?
See, if you know for a fact that a subatomic particle was at rest, one, it's a point charge, and two, it's not like finding, I don't know, like rice grains or things like that. It's a subatomic particle. It is really, really, really tiny. No one has ever observed an electron directly with their eyes in history at all. So the way you figure out if electrons are present and what they're doing, all their actions, how they're moving, all of that is one by theoretical calculations, and two, based on the effects that they may have on an electric field or a magnetic field, or what kind of results they give in a spectrometer, what kind of spectrum you're getting. So it's all by indirect methods that you observe it. So that way, like, think of it in those terms. So you can't, if you know that electron is at rest, like you can figure out that, because you have that particular element or something that's giving out the electron in a box, you can be like, yeah, I know that there is an electron in this box and it is at rest, but I don't know where exactly it is. It's that kind of a situation.
Okay.
Yeah, like, yeah. All right. Now coming back to the quantum numbers. So yeah, as I said, so Schrodinger's wave equation gives a series of wave functions. So functions are basically they're like mathematical representations of where on an electron can be around the nucleus. Okay. So these functions, they follow a pattern, like so like there are a series of equations, they're not random, and that series is controlled, or it is basically characterized by these three important numbers, these three quantum numbers. Yeah.
These are like notes I've written for the principal quantum number. Number of allowed orbitals is equal to n square. What does that mean?
So n is the principal quantum number, right?
Yeah.
So n is the principal quantum number, and yeah, we were discussing this in detail last time. So let me get the chapter notes out, all the points written there. Okay. So all the things, so again, quantum numbers decide, they characterize where all an electron will be, right? So from now onwards, think of these things as like structure of atom as trying to figure out the address of an electron. Okay. So if I were to find your address, if I want to send like, a gift package to you guys, and if I want to find your address, how is your address structured? Like, what all do I need to know?
So that number, society, location, and pin code.
Right. First, I need to know what city you're in, or okay, I know all of you are in Mumbai. Like, I need to know what area of Mumbai you're in. Like, are you in Andheri? Are you in Borivali? Are you in Khar? Are you in Juhu? Like, where exactly in Mumbai you are in? And within the locations, within the areas, I need to know what exact street you're in. And once I know the street, like a particular street can accommodate only like certain number of buildings. A bigger street will accommodate more buildings. A smaller street will accommodate lesser number of buildings, right? So within the street, I need to know which building you're in. And within a building, I need to know like which house you're residing in. So think of the quantum numbers as giving you the address of an electron. So we know that, okay, like city is the atom itself. So within the atom, you have so many different shells. Like all the electrons are arranged in different shells. And which shell it is decided by the principal quantum number. So that's what it is. So the principal quantum number determines the size and to a large extent the energy of the orbital. So size of the orbital, so it decides at what distance the electron is going to be found in. Okay. So now each of these shells or each of these orbits have they have further subshells, just like how an area has different number of streets, and then the size of the area will tell you how many streets will be in that area. So just like that, the principal quantum number will also decide how many subshells or orbitals that it might contain. So n equal to 1 only contains 1 square, which is only one subshell, one orbital. N equal to 2 contains 2 square, so it contains like 4 orbitals. N equal to 3 contains 3 square, so that contains like a total of 9 orbitals. So that's what it means. So n decides the size of the shell, and in turn, like based on the size, you can figure out how many orbitals it is capable of containing.
Like in the class when we were discussing this, so like ma'am asked what is the function of the N shell, and I answered the number of orbitals, and she said that that's wrong. So
the number of
it's just-
allowed orbitals. Okay. So what did she say? Like, what was the correction?
She said it's N only decides the shell number.
Yeah, n is literally the shell number. And yeah, like the number of allowed orbitals is given by n square. I mean, that is a fact, that is a truth. But yeah, the main thing is it decides the shell size. So this is like a consequence of it. As n increases, the number of allowed orbitals also increases. Okay. Next, so that's the main principal quantum number. Then comes azimuthal quantum number L. So L is also known as orbital angular momentum or subsidiary quantum number. Okay, other names to it. But the main importance of L is that L defines the three-dimensional shape of the orbital. Like, okay, n tells you at what distance it is. L tells you how exactly it is. Like, is it a square? Is it a cube? Is it different shape? So yeah, L defines the shape of the orbital. Like, yeah, you don't have like cubical electron clouds, but yeah, these are the 4 main shapes of the orbitals that are found in an atom. Okay. Yeah.
What is the difference between orbital and subshell?
I'll come to that. So when we discuss magnetic quantum number, the next one, like it'll become clear. Okay. Yeah. So L, okay, so depending on the value of L, like each subshell also has a name. So if L is equal to 0, that's called the S subshell, like S orbital. Okay, P orbitals. Difference between orbitals and subshells, I'll make it clear. I'll tell you guys later. But yeah, when L is equal to 0, that denotes S. L equal to 1 denotes P. L equal to 2 denotes D. And L equal to 3 denotes F. And as for the shape of the orbitals, I'll show you guys the 3D shape of what they look like.
Ma'am, what is the difference between orbit and orbital? I mean,
Orbit
there was
is
a
the
question.
big one. Orbit is the shell itself. So orbit is what n represents. Orbitals are like the smaller substructures within a whole orbit.
If we had to define it then.
Let me complete this whole section, and once the understanding is like clearer, I'll give you guys like what is the exact statement.
Okay.
Okay, so this is the, yeah, so it like, this is the shape of the S orbital or S subshell. It is completely spherical, equal likelihood of finding electron in all directions. Okay, so the probability distribution, like this is what it basically looks like. It is just, yeah, it's a spherical thing. So this is the probability distribution, and this is how it's like theoretically represented for sake of convenience. Okay, then P orbitals. And you can see, you know, difference between 1s, 2s, 3s is basically when n equal to 1, it is a tiny s orbital. When n is equal to 2, it is larger. When n is equal to 3, it is like the largest. N decides the size, L decides the shape. So you can see that all of them are S, so the shape is same, but because n value is changing, their size is changing. That's the difference or importance of S, n and L values. P orbitals basically look like this. Px, Py, Pz. Okay, why we have these three things, it'll get clearer in the next like magnetic quantum number. But yeah, so this is like the basic shape. You can see that the shapes are all the same, just that the orientation is different. One is vertical, one is horizontal, one is in the Z direction. That's the only difference. But the basic shape is the same. You can see that it's like two large bulbs. It's called the dumbbell shape. But yeah, this is the shape of P orbital. Two balloons held together this way. Okay, that is the basic shape of P orbital. Next, D orbitals. So basically, you have P orbital, split those balloons, and then you get the D orbital. So it's called the double dumbbell. You can see it from all directions. So it's like, yeah, 4 orbitals just aligned this way. This is the shape of the D orbitals. In different
What
ways.
is the axis?
I'll come to that. Yeah. So D orbitals, 4 of them, the shape is same. Only one particular DZ is a different shape. Yeah. And
So S is 0, P is 1, and D is 2, and F is 3, right?
yes.
Okay.
So F
So
orbital.
ma'am, for any value of n, like we say L is 0 to n minus 1. So for n1, only S is possible if n is 1.
Yeah. Only S is possible. It's so tiny that it can't accommodate more than that.
So similarly for n2, only till 2p it is possible. Sorry, yeah, till 2p.
Yeah, till P, S and P. Okay. So this is the shape of F orbital, like more complicated than D orbitals, more like a flower shape kind of. But yeah, this is the shape of the F orbital. So I'll send you guys this link. If at all I forget to send it, remind me. I'll send it on the group. You guys can check it out. You can play around with it. You can explore. Okay. Gives the simulations of different atomic structures, orbitals, and all that. We'll keep coming back to this site. Okay. So that is basically the importance or significance of L. It gives you the shape of the atomic orbitals. Like quantitatively, it basically gives you the angular, it tells you the value of the angular momentum. It's a formula to it. Restrictions, again, the value of L depends completely on the value of N. L will range from 0 until n minus 1 for every value of N. Okay. So there you go, subshell notation. So when n equal to 1, only 0 is possible, so that you only have 1s. When n equal to 2, 1 and 0 and 1 are possible, so you've got the 2s and 2p. When n equal to 3, 3 values are possible, 0, 1, 2. So you have 3s, 3p, 3d. And then when n equal to 4, you have 4 values, 0, 1, 2, 3, 4s, 4p, 4d, 4f. That way. Yeah.
That should have been 2p, right? Not 3p.
Yeah, this should be 2p.
Yeah.
Typo. 2p, uske baad 3s, 3p, 3p. Next comes M. So this is something we hadn't discussed last class. The third quantum number is the magnetic orbital quantum number, or also called magnetic quantum number, noted by M. So this magnetic quantum number gives information about the spatial orientation of the orbital. So L gives you the shape, right? So M gives you the spatial orientation. So what do you mean by spatial orientation? Like, what do you think that represents? What does that say?
Does it have to do anything with how it, like how we visualize it, like spatial?
How we visualize, I mean, it's telling you the shape is basically how you can visually see it, like that's the shape. So how is spatial orientation different from shape, or how is it adding on to the shape?
Does it tell you how far away from like the nucleus it is?
That is n, that is the principal quantum number, right?
How many electrons can be in that area?
How many? In a way, yes, but that's given by n square and that's given by L also. Like you have SP, SPD, all of that stuff. Now focus on the word spatial orientation.
How much space it occupies?
Close. Spatial is like, okay, space related, not like outer space, like literal space related. Orientation kya hota hai? You guys have come across the word pehle, like obviously your school orientations hote hain. Apart from that, like what context, like what does that word orientation contextually, what do you understand by it?
Categorize maybe.
Close, kind of. Now, when you call it spatial orientation, so it's basically telling you how it is arranged in space. So
Oh, is it its structure?
structure, like the whole thing together is the structure. So think of it this way. So the first quantum number n is telling you how far from the nucleus it is. And then from L, it's telling you what shape it is. And then M is telling you how that shape is oriented. So that's where Cavalier axis comes from. So spatial orientation in the sense, is it in this direction? Is it like this? Is it like this? Is it like this? Like all that stuff. Like how is it? How are the orbitals oriented with respect to each other? Are they at an angle? Are they completely perpendicular? Or are they parallel? That kind of orientation. Okay.
The origin of the axis, is that the nucleus?
Yeah. So the origin of the axis is assumed to be the nucleus. Okay. So I'll do the theory first and then I'll go back to the atomic orbital. It's like visual. Okay. So just like how, so for a particular value of n, you had a range for the values of L, right? So L ranges from 0 to n minus 1. So you're going one step further. M ka values is again decided by the value of L. Okay. So the value of M, magnetic, this thing, so M, or sometimes you'll also look like see it represented as ML. So this is the magnetic quantum number. So this gives the spatial orientation of the orbitals. Spatial orientation matlab, you know the shape. Now how do you need to keep that shape? Like vertical, horizontal, at an angle? How exactly? And the range of values lasts from minus L across 0 to plus L. So for example, for S orbital. For S orbital, what is the value of L?
0.
0.
0. Yes.
Like
Which means
1.
that M can be equal to
0.
So that will be 1, right?
minus plus kuch nahi hai, only 0, so just 1. For P orbitals, L ka value is 1. So what all M values are possible for P?
-1, 0,
Minus
and
1,
plus
0,
1.
1.
0 and -1.
Correct. -1, 0, and 1. So from minus L till plus L. For d orbitals where L equal to 2 minus 2, L equal to 2, what are the possible m values?
-1,
Minus
Two,
minus
two,
2 minus 1 0 plus 1 plus 2.
1 and 2. So Kaveri, you always start from minus L.
Yeah.
Rega, then you won't like miss out on anything. Okay.
But ma'am, if we take it as 0, like how can we say that the spatial orientation is 0?
This does not represent like physical quantities like dimensions or anything like that. It's just quantum numbers. They're just numbers given to that particular thing. Okay. And
So
then
if we're told to write m, so we list all this.
yes. And F के लिए L का value is 3. So what all
-3 to +3.
yes, -3, -2, -1, 0, and 1, 2, 3. Okay. So each of these values represents a different orientation of this orbital. So for example, if I take P, how many orientations does P have?
3.
3,
Huh? How many, Rishad?
3.
3. You have
Three.
-1, 0, and +1, right? Which means that the p orbitals, which have a dumbbell shape, you can arrange them in 3 different directions. So that's what the axis represents. So typically, if you take any one of these to be, let's say, the z-axis, the first one, let's say it's oriented along z-axis like this, then the other 2 are represented perpendicular to z-axis. So if this is z, then perpendicular, let's say if this is y, one p orbital will be like this, and the third p orbital is going to be along the x-axis like this. Yeah, so all 3 of them.
That's the
are,
z-axis or the x-axis? The last one that you chose.
Oh, this is x. This is y. I just assumed it to be like this. Any axis can be in any way. Again, this is all man-made. It is like a social construct or a mathematical construct that is supposed to help you put labels to things so that it's easier to like talk about it. But essentially, like x, yeah.
If we're given the, like if we know the magnetic quantum number and we be asked to draw this stuff.
You may be asked. It's pretty simple, right? Like 3 different directions. Just ensure that all 3 are like perpendicular to each other. And yeah, each one will be along one single axis this way.
How do you know which axis is y, which one's z, and which one's x?
Yeah, so that is the thing. This is like a social man-made construct. It's like mathematics. It is up to you. The important point is that x, y, and z, all 3 are perpendicular to each other. And again, this is all, it's just spatial orientation, right? Like let's say these are my 3 axes. If I say my thumb is x, this is y, this is z, I can just like turn this around like this, and then all of them change directions, x, y, z. So yeah, like the main point is that x, y, z all need to be perpendicular to each other. Essentially, the 3 of the p orbitals representing -1, 0, and +1 are all perpendicular to each other. But it's not like fixed that x is -1, y is 0. ऐसा कुछ नहीं है. Just that 3 values of p are there. They represent the 3 orientations of the p orbitals, and the 3 orientations, like how are they oriented? All of them are perpendicular to each other. That's what it is. Yeah.
Like if there are 3 orientations in the p ka case, so in each one there will be 2 electrons. So from that, multiplying by 2, we can find out the total number of electrons, right?
Absolutely. Exactly. So
in each of the orientations there will be 2 electrons.
Correct. So each of the p orbitals is capable of handling, or like it's capable of accommodating 2 electrons, maximum 2 electrons. कुछ cases में 8 भी हो सकता है, but yeah. that will come to it when we talk about the electronic configuration. But for now,
P will always be assumed as having 6 electrons.
not necessarily. The maximum it can take is 6 electrons.
Okay. Yeah.
Similar to Kaveri's doubt. So the value, for example, L is equal to 0.
Mhm.
So that really does not, specify as shape. This is just given to it like that, right? So 0 is, I think, spherical, or what was the shape? If L is equal to 0?
L equal to 0, S orbital is spherical.
Spherical, yeah.
This is
So
perfect.
that is just the number, right?
Yeah, that's just a number. That's a number in the equation. The whole equation taken together represents that the electron exists in spherical, like the electron cloud is spherical in shape. So that way, like if you observe, S ka shape we saw earlier is spherical. Now, if you have a round sphere, does sphere have like multiple orientation? Does it look different if you change the direction? It's like a circle, right? Like you won't even figure out if I turn it 180 degrees or 270 degrees or, like single orientation. And there's only one single M value for S spherical, this thing. Yeah. But for P orbital, like this particular shape, it can be arranged in multiple ways. Like that's why you have these 3 orientation that exist for P orbitals. Similarly, D orbitals have multiple listing. So the 3 orientations, depending on which axis the particular P orbital is in. So each of, like there are 3 of the P orbitals, right? So these 3 P orbitals are represented as Px, Py, and Pz. So you can't have 2 Px's and 1 Py because obviously, like in one particular axis, only one orbital can exist. The other one, electronic will repel each other. They can't occupy the same space. That's why they're all like perpendicularly arranged to each other. Similarly, D has 5 orbitals, -2, -1, 0, 1, 2. So the names for all of them are, you have dxy, dyz, dxz, then you have dx square y square and dz square. These are like the names given to the orbitals. And I'll show you the orbitals and it'll make sense why they are given these particular names. And F has a total of 7 orbitals. And yeah, each one corresponding to each of these M value. So
So this X, Y, and Z is nothing related to the axis they are in, right?
No, it is completely related to the axis they are in. X, Y, Z represents the 3D axis.
Okay. So Px is then in x-axis and Pz is in z-axis. So it's like that.
Correct.
Okay.
So that's what it is, right? It's giving you the spatial orientation. And from what you guys remember in coordinate geometry, what is coordinate geometry used for? Your XY axis?
Locating stuff.
Locating.
Pinpointing stuff.
Yes. So this is like a real life application of it. Like your orientation or directions of your atomic orbitals are decided by your 3D axis. So 9th, 10th May, you guys had studied about it's a 2D thing that you guys did, only X and Y axis. You could do it completely on paper. Abhi 11th, 12th May, you guys would have 3D geometry. I think you guys already did some bits of 3D geometry, like physics may, did you guys work with vectors yet?
We did.
Yeah.
You
Yes,
did.
ma'am.
You work with vectors, right? So you've got your I cap, J cap, K cap. They represent the 3 directions, X, Y, Z.
Yes.
So once you guys are like done noting this down, points about M, the range, and possibly like the values for different subshells, I'll switch to the other screen. So Kaveri, you done? Sana, is it done? Adit is also done. Okay. Smira done. Rishit and Arnav? Okay. Cool. So did you guys watch that parody of Shape of You song?
I did. I saw the whole video.
You did. How much of it made sense?
It actually made sense, to be honest.
It did. Awesome.
Yes.
This chapter and the next one, chemical bonding, is also going to touch about, like how these atomic orbitals interact with each other and all that.
Ma'am, this is the biggest chapter we're gonna have this year, right?
This and chemical bonding. These two are biggest, and there's one more towards the end of the year, equilibrium. That's another brain heavy chapter.
So is chemical bonding like numericals or theory?
Chemical bonding has less of numericals, but conceptually it's like structure of the atom. So just like,
okay.
yeah, that's literally structure of molecule. So now you learned about atoms. Now let's figure out how atoms combine together to form molecules.
So it's basically just information, bit of application and more information.
No. Yes, information, but it's more application than of that information rather than knowing the information.
Okay.
It's all going to be extreme.
Questions on this chapter would be application based or like theory?
Both of these going to be application based. I would say about 80% application, 20% chance of theory. And even your theory is going to be like state Heisenberg's uncertainty principle and things like that. Not like really long ones. Only in inorganic, you guys are going to get like theory based thing. Like rest of the chapters, it's all application. Maximum theoretical questions you're going to get is like a give reason kind of question. All right. So orbitals. Again, starting with s orbitals. So you can see that s orbital, there's only one m value, which is 0, which is why, like no different orientations. All of them are going to be spheres only. Whatever direction you take it in, you can see that these axes are revolving. It's all the same thing in any direction. Next comes p orbital. So your basic p orbital, okay, this is like the 2D representation. So each orbital in different direction, x, y, z. So px, py, and pz orbitals. So yeah, this would be your px orbital because this is aligned in the x axis, the red color axis. So your py orbital will be aligned in the y axis. So the vertical axis is the y axis, aligned along the y axis. So this is py. And pz, you can see that kind of looks like x axis, but it's actually perpendicular to the x axis. Like because it is turning, it's similar to this. So this is px, py, pz. Yeah, theories like notes are given here. The p subshell. So yeah, you guys asked about difference between subshell and orbitals, right? So the L equal to 0 as a whole is a subshell. L equal to 1 as a whole is considered as a subshell. So within the L subshell, you have 3 possible orientations. So each of these orientations, px, py, pz, is considered like a single orbital. Yeah. So that's why we say that L equal to 0 has 3 orbitals. One orbital, L equal to 1 has 3 orbitals. The 3 orbitals are px, py, and pz. So together they are called the p orbitals. So you can see here the 3 p orbitals are aligned along the perpendicular axis.
So by that logic, doesn't L decide the number of orbitals?
L decides the shape. And
But if we have, sorry, not, L only, azimuthals, quantum number. If you just said now that the number of
N decides the number, yes. I'll come to that. So that's another, like, how do you connect it to n squared? I'll tell you that. So here, the p subshell can hold a maximum of 6 electrons as there are 3 orbitals within the subshell. So the 3 p orbitals in the p subshell. So you have shell made up of subshells SPDF, and each of these SPDF has like a number of orbitals. That's what it is. The 3 p orbitals are at right angles to each other and have a lobed shape. So each of these is called a lobe. Size of the p orbitals also increases as the energy level, the value of n, the first principal quantum number, increases. Okay. Next, let's look at d orbitals. Px, py, pz is pretty straightforward along the axis. You get that. Now, d orbitals, there are 5 of them. How do you figure out which is what? Okay. So d orbitals have a double dumbbell shape, right? Like it's like 2 or p orbitals put together, kind of, right? So if those 4 lobes are aligned along the axis, so that's denoted as x square, y square. So let's say, so let's say these are the 3 axes, putting it in black. So if you have d orbitals where the lobes are along the axis, so the lobes and axis fall on the same line, so that is established as dx square y square. That's like decided. Now, if they are between the axis, so if it is in between the x and y axis like this, the blue parts of it, the blue one I'm drawing. So this is the x axis, this is the y axis. They are between the x and y axis. So that one is denoted as dxy. If it is between y and z, like this, like if it is aligned at 45 degrees from the axis, if it is between the 2 axes, then that's dxy, dyz, and dxz. So that way there are 3 of them in between the axis. If they're along the axis, so that's dx square y square. And then if it's like a completely different shape, like you have it's along the axis and then it has a tire in between, so that is represented as dz square. So these are like 5d orbitals.
Ma'am.
What is the signal? Okay, Kaveri, go ahead.
No, go on.
Okay, so ma'am, how did the x square and y square emerge? Like, is
Square
it
and y
because,
square, nahi, the name itself is called dx square y square.
okay, so how did it exactly come? Like, how did the square come in?
So it's not like a mathematical formula, it's just the name given to that particular orbital. How the name came about, that's an interesting question that I don't know. Either it's convention that everybody agreed to it, or it's related to the wave equation of that particular orbital. It's one of these two cases. But yeah, x square y square is the name given to the d orbital, which is, where the lobes are lying along the axis. And if it is in between the axis, like axis either hai, but it is in between them, it's along, it is on the 4 quadrants, then depending on which quadrants they are in, they are either dxy, dyz, or dxz. And if it's like, just completely along the z axis with a tire in between, so that is dz square. I'll just click on this. So this is dx square y square. You can see it rotating, the z-axis like peaking from in between. So it is lying along the axis. Upper vertically it's the x-axis, horizontally it's the y-axis, but yeah, it's like that. This is the other one. So this is dxy. You can see that along the axis there is nothing, but in between the axis, like on each of the quadrants, the lobes are arranged. So this is dxy. Because it is between x-axis and y-axis, it's called dxy. If they are in the quadrants in between x-axis and z-axis, like y-axis pe kuch bhi nahi hai. If they are in the quadrants between x and z, so you can see it here clearly. So x-axis and z-axis is here, and the lobes are in these quadrants. So that is dxz. And then if the lobes are like in the quadrants of y and z, so you can see y or z ke beech mein hai. So this is dyz. And
Ma'am, this is for the D. This is for D, right?
yeah, this is all d. That's why it's
So in D there will be 5 orientations, right?
yes.
So what about the ones that are actually supposed to be on the axis?
No, it doesn't exist. Like this is how the d orbitals are arranged.
Oh,
Yeah, these are the
I
5.
thought it has to be on that.
So that's how the p orbitals work, and this is how the d orbitals are arranged. So this is
Oh,
dz
ma'am, I
square.
didn't understand something.
What's up, Sanat?
Like the first one and the last one, why do they have squares in them?
That's just the name given to those particular orbitals.
Oh, so like it doesn't have anything different, right?
No. Like obviously it has its orientation different, but yeah, that's the name given to it. So if it's like along one axis, usually conventionally considered as z-axis with a tire in between, so you can see that it's perfectly symmetrical this way. So this is dz square. This is d x square y square. You can see that it is along the axis. So x-axis and y-axis are like this. It's not in between, but this one is in between the axis. X-axis, y-axis, you can see it clearly over here. And the lobes are in between the axis. ठीक है? All it is clear about the different d orbitals. Got it? Okay.
Wow.
Hmm?
Understood. Now.
Okay. Yeah. F orbitals, there are 7 of them, and they are a lot more complicated than p and d orbitals.
Could you go back to the D ones for 1 second? I forgot
Yeah.
to write down.
If you're curious, these are the names given for the F orbitals. We'll come back to it. Just switch to the d orbitals. Any specific one that you want to look at, Kaveri?
No, just the names, just the DX.
So you have dxy, xz, and yz. Dxy, yz, xz be cyclical. And then you have the dx square, y square, and the dz square. I have a hunch it probably comes from Schrodinger's equation. Like when the NLM values, you put it specific for d orbitals. Maybe the x, y, z parts of that equation represent these things. Maybe. So yeah, the 5 orbitals, m values are 0, plus minus 1, plus minus 2. So you want to look at the f orbitals?
Yes, ma'am.
So these are like the 7 f orbitals. So their names are a lot more complex. M values we discussed 0, plus minus 1, plus minus 2, plus minus 3, right? Ranging from minus 3 all the way to plus 3. So f orbitals, a lot of unstable and really rare elements contain f orbitals. Atoms got to be really big for filling of f orbitals. The general set, okay, these are like the names given to the different f orbitals. When m value is 0, that is called mz cube. Plus minus 1, you have xz square and yz square. Plus minus 2, you've got this xyz, whatever, and plus minus 3, you've got this. These are really complicated. Like this is definitely not there in your syllabus because we studied about SPD. I figured I'll just do this. Ritu, if you do that, you're not gonna mess with the scientists, you're gonna mess with the students who will have to study that.
It's gonna be so much fun.
So yeah, different orientations. Kind of like reflects the d orbital, just like a really more complicated form of d orbitals.
The names aren't written.
Names are there, let's scroll down. These are the names of f orbitals.
We note this down.
Oh yeah, this here it's not written. No.
We have to note the names
Are
down.
the names part of our portion? Like, will they ask it?
Part of the portion you don't have to.
So we don't need to know, right?
You have only till SPD. F usually textbooks say it's really complicated and all that. But for your information, just for the sake of symmetry, because we read about SPD, showing you the F orbitals. Okay, so this gives you like 90% of the address of an electron. So with N, you can figure out what shape, like how far from the nucleus it is, like the rough area. With L, you can figure out which subshell it is in. And then with the value of M, you can figure out, okay, what is the orientation of it. Okay. So you basically created the location, you created the streets, you created the buildings of where the electrons can be situated. So now how do you accommodate the electrons? So that would be our next part of it.
Ma'am,
What a number M.
studying these all, Where exactly in real life does this apply? I mean, yeah, sure, it is a concept that we are learning, but where exactly in real life can we apply these all?
This
In
is
which,
real life, Rishit. This is the structure of the atom.
yes, but I'm like, it's only when you're a scientist or something, but in which field can this really come in handy?
Uh, any science-based field, I would say. This is like the foundation of chemistry. Like the properties of these orbitals tell you about how metals behave versus how non-metals behave, how chemical bonds are formed, why certain bonds are unstable versus why certain bonds are stable, which in real life would have applications if you want to go in like any science base, be it construction, like polymers, food technology, anything that deals with materials and chemicals and things like that. This is all gonna play a role.
How much more of the chapter is left?
Almost done. So after this, we talk about the electronic configuration and that's it. Okay. So these are like the three quantum numbers. Now the final quantum number that tells you like how exactly the electron is arranged, like how are you going to put the electron in each of the rooms of the building, is given by the spin, which is S. So this is not part of Schrodinger's wave equation, but this is an important quantum number. And spin basically decides the magnetic properties of the material. Like why iron is magnetic, but like chlorine is not, for example, that sort of thing. So electrons also spin about their own axis. A particular orbital, like any orbital, whether you take px, py, whether you take pxy, any one specific orbital can hold only 2 electrons. It should be up to 2 electrons. Like it can hold either 1 electron or it can hold 2 electrons. Okay. So when you put 2 electrons in the same place, what do? Will they be happy? Like, will they get along with each other?
They will repel.
They'll repel,
Yeah,
right?
they'll repel because same charge.
Same charge. So you'll have to accommodate in a way where they don't interact with each other. So that's when the spin comes into picture. So the 2 electrons that are held in any particular orbital, they would have opposite directions of spin. So if one is spinning in clockwise direction, the other one is spinning in anti-clockwise direction. Okay. So opposite spins. So that way, each is doing their own thing. They don't interact with each other. No problems at all. So these spin states are represented by the 2 values. So spin S, also represented as ms, has 2 values. Either it can be plus half or it can be minus half. And visually, each of these spin is represented with a upward arrow and downward arrow. It's not like, again, these are all representations. It's not like upward arrow means clockwise or counterclockwise or downward means a specific direction. It doesn't stand for that. These are purely just representations. The main thing is that...
Why half?
So one is a positive spin and the other is a negative spin, plus half and minus half.
Why the half?
Why half specifically? There is a reason for it that I'll check it and I'll let you guys know in the next class. Or if I can find a written this thing about it, I'll send it to you guys.
Is it because it's like one part of 2? Because each have only like one orbital has 2 electrons.
Kind of, but these numbers don't represent like any certain quantity. Like that could definitely be a logic, like single orbital plus half minus half, they cancel each other out. But again, speculation. I let me look up the exact reason and I'll tell you guys. But the main
Ma'am, that's a typo, right? In the diagram, both
yeah.
have plus half.
No, one should be plus, one should be minus. So the main thing is that electrons, like 2 electrons occupying the same orbital, spin in two different directions, opposite directions. If one is clockwise, the other is anti-clockwise. And the way you represent it in books in general on paper is one with the upward arrow and one with a downward arrow. And of course, like this is again a quantum number, right? Just like how we figured that n can range from 1, 2, 3, 4, and L has certain values from 0 to n minus 1. M has values from minus L to plus L. That way, S can only take two values, either it's plus half or it's minus half. So these are your 4 quantum numbers. Oh, summary.
But-
Yeah.
Ma'am, so if they move in the opposite direction, they will eventually meet, but they will repel, right? So that is the logic which they are going
That
with.
will never meet, Rishad. No.
But they are going in the opposite direction, right?
Opposite direction doesn't mean like that they have opposite spins. Like one is spinning in clockwise, the other is spinning in counterclockwise. They will never ever come across, like they will not come across each other's path. Again, these are subatomic quantities, Rishit. Don't think of them as spinning balls. Like that would be a wrong representation. Again, these are electron clouds. You don't know exactly what they are like, what they are, but yeah, like opposite spins.
Ma'am, I have a doubt. So
Yeah.
like all the other three numbers, they're interdependent or interlocked, like interlinked, right?
Yes.
So is this one also like depending on something?
No, just plus half or minus half, just two values, opposite values. That's it.
Okay.
Okay. And these 4 numbers put together will give you basically the address of any electron present in an atom. Again, because if you think of it as address of an electron, the main check is that any electron in any particular atom of an element, no 2 electrons can have the same address. Like 2 electrons cannot occupy the same place. So that is like your, if you're doubtful when you're writing the quantum numbers of a specific electron, you need to check that they are all completely different. Quick summary, this is what we had studied. N defines the shell, determines the size of the orbital, and to a large extent, energy of the orbital. So the energy values that we say when it is going transition states and all that, that is decided by the N value. There are N subshells in the Nth shell. L identifies the subshell and determines the shape of the orbital. There are 2L plus 1 orbitals. So this is like 2L plus 1 orbitals. So if L equal to 2, then 2 into 2 plus 1, 5, which is what your, d orbitals ranges. There are 5 orbitals. So there's 1 s orbital for L equal to 0, 3 p orbitals for L equal to 1, so your px, py, pz, 5 d orbitals for L equal to 2, so your dxy, yz, xz, x square, y square, dz. And to some extent, L also determines the energy of the orbital in a multi-electron atom. So other than hydrogen, if you have any other atom, obviously that has multiple electrons, right? So N is the first one that decides what the energy value is. But we found that in a specific shell, multiple electrons can exist. So within the shell, if you have to differentiate which is lower energy, which is higher energy, then that is decided by M. So M designates the orientation of the orbital. So for a given value of L, ML has 2L plus 1 values, the same as the number of orbitals. So each M value corresponds to a particular orbital assumption. It means that the number of orbitals is equal to the number of ways in which they are oriented. How they are oriented in space, spatial arrangement, spatial orientation.
So what exactly does 2L plus 1 give?
2L plus 1 will give you how many orbitals there are. Yeah, Sanat, you are saying?
I was saying it gives the total number of orientations, right?
Yes. Total number of orientations, in turn, total number of orbitals. Like each orientation is a separate orbital. Like Px is one orbital, Py is one orbital, Pz is another.
Ma'am,
Yeah.
would the total number of orientations just be was it M? Yeah. No. Yes, M.
No, M has a range
Total
of
number of
values.
But like if we do -1, 0, and 1, so we have 3 orientations. So that will be the total orientation.
Yeah, but M is
So
minus
it's
1,
12
0,
plus
1.
1. No. Means
Like you get like what is -1, 0, and +1. So that's the M values. So for L equal to 1, you have M equal to -1, you have M equal to 0, and you have M equal to +1.
no, I meant if M that's -1, 0, 1, that's 3 orientations, right? For P, if we're talking about P. So
Yes.
you've got 3, right? Px, Py, Pz. So then what is 2L plus?
How are you getting, where are you getting the 3 from? So this is like a formula to tell you like how you got it.
3 we're getting from -L to L.
Yeah, so you've like if you count it, you'll get it this way. Without having to count, if you just do 2L plus 1,
Acha, acha.
it'll be like 2 into 1 plus 1. So that's 3 that
Yeah.
way. So that's what it says. So you get it that way. Okay. How do you connect it back to n square, right? All right. When n equal to 1, the first shell, what all L values can it take? Or let me just make a table. So let's build possible things like possible electronic structures. Yeah. So you have N, L, and M. So the first is when N equal to 1. What all values are possible for L?
0,
1 value 0.
L equal to 0, 1 minus 1. And what all values of M are possible?
1, 0.
Only 1, M equal to 0. So L equal to 0 represents this is the 1s like orbital, and there's only one orbital, so it's represented by one box. Okay. When N equal to 2, what does L represent? What are values are possible for L?
0 and 1.
L equal to 0 is possible, L equal to 1 is possible. So L equal to 0, what is the name of that particular subshell?
Yes.
Yes.
So because N equal to 2, this is the 2s subshell, and this would be
2p.
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 subshell, yes. Abhi 2s ke liye, what are the possible values of M?
Again 0.
0. And 2p ke liye, values of M?
-1,
1,
0,
0,
plus
1.
1.
Yes. So these three, when you're doing electronic configurations, they're represented by 3 boxes. So 2s is represented by a single box, one this thing. These 3 are represented by 3 boxes. N equal to 3. What all possible values of L?
0, 1, 2.
0, 1, 2.
0, 1, and 2. So N equal to 3, L equal to 0 is which orbital?
3s,
3s,
3p, and 3d.
3p, and 3d. Okay. For 3s again, M एक ही value. 3p again, -1, 0, and +1. And 3d, you have -2, -1, 0, +1, +2. Okay. So M equal to 0, this would be the 3s. 3p is again 3 orbitals. 3d there should be 5 orbitals. Okay. Now, for each case, check 2 things. One is the number of orbitals and the number of electrons. Is the rightmost end visible to you guys?
Yes.
Yes, ma'am.
The number of electrons part.
Huh.
Yeah.
Okay. So in the first, for n equal to 1, how many orbitals exist in n equal to 1?
1.
What is the total number of orbitals for n equal to 2?
4.
Yes, so you have 1s, so this is 1, and this is 2, 3, 4. So total 4 orbitals. Similarly, how many orbitals in n equal to 3?
9.
9.
9.
Yes, 1 plus 3 is 4, 4 plus 5 is 9. So do you see the pattern here? Like the relation between the value of n and the number of orbitals?
It's squared.
Yeah,
Yep.
squares of natural numbers.
Yeah. So that's where that that statement that we saw earlier, the total number of allowed orbitals is given by n squared. That's where it comes from. Okay. So now
Let's
let's
draw this table.
Not necessary, because for electronic configuration we'd be doing that anyway. If you want, you can draw it. Otherwise, we'll be doing this for electronic configuration. Okay.
Ma'am, is n square also used for number of subshells?
No, because number of subshells is given directly by n. Number of subshells is like this has n equal to 1 has 1 subshell, n equal to 2 has 2 subshells, n equal to 3 has 3 subshells. That way.
Okay.
Yeah, but like you don't really use that so much. Like you will be making a lot more, you'll be using individual orbitals a lot more than the subshell as a whole. That is why this is more like, that's why we talk about orbitals a lot more than individual subshells. All right. What is the maximum number of electrons that can fit in n equal to 1?
2.
2. One up spin and one is down spin this way. This is how electrons are represented. Okay. When both of them are there, you just draw half arrows. When there's only one electron, then you draw a full arrow. This is how electrons are represented when you're filling up the orbitals. But we'll revisit that in electronic configuration. Okay. What about when n equal to 2? How many electrons total?
8.
8 electrons.
8 electrons. So इसमें 2 and 6 total in this. 2 plus 6, 8. How many in the third shell?
18.
18. So 9 orbitals. Each orbital can take 2 electrons. So that's a total of 18 electrons.
Ma'am, one.
Ma'am, why have you drawn half for everything?
Because there are 2 electrons occupying it. Like this is how it is usually represented, the convention. So if it's a fully filled orbital, it is represented by 2 half arrows. If it is a half filled orbital, then the single electron is represented by 1 arrow. That's the convention. That's how it is represented.
Okay, ma'am.
So this is,
I may have a doubt.
yeah.
I remember that when we were doing like the periodic elements, when we were seeing the configuration, it goes 2, 8, 18, 8. So how does it come down to 8 again?
Good catch. That question will be answered in like the next half an hour when we do electronic configuration.
What's the question?
So in each shell, as we fill it up, we're getting 2, 8, 18, right? But grade 9 may, when you are doing electronic configuration, like for example, if you do calcium, the one that you learned was 2, 8, 8, uske baad 2. Aise continue ho raha hai na? So how does that make sense? Like, why is there 8 coming over here? That's what she asked. But it's good that you brought it up, because do you guys remember these numbers? Do these seem familiar to you from whatever you studied way back when? Grade 9?
Yes.
Yeah. So that 2n square ka story behind it, the logic behind it, where it comes from is from this whole thing. So that's why you're getting these specific numbers. Okay, it all comes down to these quantum numbers. Okay.
So ma'am, we'll only learn till n is equal to 3.
N equal to 4 bhi aayega, but yeah, till n equal to 3 is the most significant, the most important.
Okay.
But like once you get the logic behind it, you can build it up till like 108, 110 also. So.
Ma'am, as per what I remember, so if it was 2, 8, 8, and 8, then we go to the second shell, right? If I'm not wrong.
Not really. I don't understand. I'll have to revisit.
So if the element is more than 20, which so not more than 20, whichever element is 18, after that the atomic number is 18.
Yeah,
So after that,
yeah.
so after that, so 2, 8, 8, then we start filling from wait, yeah, no. So I was 2, 8, 8, and then the third shell is also 8. So so after basically 2, 8, 8, 8, then we start from the third shell or second shell, like after it's completely filled.
Forget about it. Like we'll do the electronic configuration now. It'll be clear. Just follow this. Like don't try to remember it. Just know this logic and use this logic that we'll be going ahead with. Okay. All right. So now that you know the structure of where all electrons can be accommodated, how it can be accommodated, and all of that story, let's start filling up the electrons. Okay. So filling up electrons follows certain rules. You've got Aufbau's principle, and then you've got Horn's rule, you've got Pauli's exclusion principle, and all of that. Okay. So the Aufbau principle states that in the ground state of atoms, like we're not talking about ions or excited state or anything, we're talking about stable, proper atoms as they exist naturally. The orbitals are filled in the order of their increasing energies. So this is important. You can't just randomly fill up orbitals. You need to fill it up in the increasing order of their energy level. Okay. And remember we said that like what quantum numbers are important for the energy levels? What gives you information about the energy levels?
Could you repeat the question?
Yeah. So which quantum numbers tell you information about the energy level?
N and L.
N and L, yes. So first N and then L. So to figure out which orbital gets filled up first, all you need to do is check the value of N plus L and then fill it up in the ascending order. Okay. So that is what Aufbau principle states. So orbitals are filled in the increasing order of their increasing energy. So electrons first occupy the lowest energy orbital available to them, and then they enter like the increasing higher energy orbitals. Okay, this is like the base rule in all of chemistry. Like just remember it for every single chapter. Stability corresponds to lower energy. So if there is higher energy, if something is of higher energy, it is less stable. Okay, so lower the energy, more is the stability. Higher the energy, less is the stability. Tends towards unstable. And every single element, electron, chemical, what have you, is always looking at wanting to be stable. Yeah. So chemical reactions happen because the energy level overall is lower, and that means more stability. Bonds are formed because energy level is lower, and that means more stability. So everything in the world, like the motivation of electrons, of atoms, of elements, is stability, which means lower energy. Okay, so just like remember it, will make things much easier. This is like the rule of the universe in a sense. Okay. All right. So electrons, because like everyone wants to be stable, right? That's the reason they try to occupy the lowest energy possible. That is the reason for, you know, the order being in the order of increasing energies. So they first occupy.
Sorry for interrupting.
Yeah.
Could you repeat the stability part? Higher the stability, what was that?
Higher stability corresponds to lower energy. So, you know, for any two systems, be it atomic orbitals or any system, basically, if one is at a higher energy and the other is at a lower energy is more stable, higher energy is less stable. That's like in general.
Higher unstability means higher energy.
Yes. Higher energy means less stable or higher unstable. Yeah.
And that's because they have to react with, that is why they have more energy, right? The unstable one.
It's the other way around. Like they get enough energy and that motivates them to react so that they can get to a lower stability. And that is the reason why some reactions happen and some reactions don't happen. If they're already like stable enough, they're like, yeah, I don't need to do anything. I'm not gonna, you know, break these bonds and put effort into it. Like that.
Is this why like your higher atomic number elements don't exist?
Yeah, they're like really hard to exist. Higher energy level electrons are less stable, and there's like a few other things at play. You know, the nucleus is unable to hold on to those electrons, and within the nucleus itself, a lot of positive charge, meaning a lot of energy, that leads to some instability. Among multiple factors, yes. Okay. So yes, that is why electrons, any electron always prefers the lowest possible energy level that is available to it, and then enter into the higher energy orbitals only after the lower energy orbitals are filled. So if there's any vacancy in the lower energy, like, yeah, I'm going to the lower energy. Okay, so now based on Aufbau's principle, let's see which atomic orbitals are filled up first. Okay. So again, this is an extension of this particular table. I'm just writing it here. So you've got 1s, second may you've got 2s and 2p. You've got 3s, 3p, 3d. So you've got 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and then do 6s, 6p, and it goes on. Okay. Okay.
No, shouldn't that be till G, 5G?
5G, yeah, theoretically yes, but practically like we don't find it. That's why I just denoted it this way.
This is part of Gauss principle.
We'll be applying Gauss principle to this now.
So now do we write this down now?
Yeah, write this down. So yeah, write down Gauss rule. I'll just put it here again, and then. So Gauss principle. Write down the statement: ground state of atoms, the orbitals are filled in order of their increasing energies. So you may highlight, underline, write it with a different color, order of increasing energies. This is the important part.
Do we have to write all 3 points?
Now just try this is
Like the first 2, right?
first one for sure. If you've already done, finished, you can write the second. But yeah, this
Okay.
is important. So once you're done writing till here, let me know, and then I'll show you what to do. We'll figure out what else, how to do the electron.
We write till 6s, right? 6p.
हाँ, इसके बाद I'll show the whiteboard, like note down what I'm writing on the whiteboard. Note it down as it is, the difference in colors, all of that.
Ma'am, I had one more doubt. So, those arrows in the box, one part, ma'am told something about there being only one at each box. What was that? So, like, what do I say? So, for example, one second, let me think. So, basically, those arrows, one in a box, you wrote 2 arrows, right? Both of them half because they were filled.
Oh, this one, like this notation.
Yeah.
Yeah, like
So,
usually the notation is when it is fully filled, when 2 electrons are occupying, you will see it denoted as 2 half arrows. Depending on the book and the printing and all, you also may come across this. But yeah, this is the more common one that I've seen.
yeah, I agree with that. Then ma'am said, there will be only one arrow for each box or something like that. So, is it
Yeah,
correct? Or
you're just like jumping around, Rishad. Like we're going step by step, right? I'll show you like let's finish up the whole electronic configuration part, and then if there's any doubt, any anomaly, like then we'll discuss it. Okay.
so that part is yet to come.
Yet to come. Yes.
Ma'am, I had a question. Like from 5, when you come to 6, like, I didn't understand how there's a decline.
From 5 and then 6, what is?
Yeah. Like 5f is there, and uske baad there is no 6f, and then how does it keep decreasing?
It doesn't decrease. Like SPDF will keep on continuing. So 5s ke baad, theoretically 5G should be there, but practically speaking, like you don't find it in real elements, which is why we jump to 6s and then 6p and then 6d and so on. Guys, you don't have to write the whole thing, just write it till here and let me know, and then we'll move on with the electronic configuration.
Write down till where?
Till increasing energy is the statement.
Ah, okay.
Okay. Yeah. And then uske niche, this is the application part of it. Have you guys noted, written this down, this whole thing? The table?
Yes.
Okay. All right. Now, don't write anything immediately. Pay attention here. Okay. So we just decided that the energy level we can figure out using n plus l. Okay. So using that, what is the energy level for 1s? What is the n plus L value you get for 1s?
2.
Kaise? What is the n for 1s?
1s is 1 only, right? N is equal to
1.
1.
N equal to 1. Fir S denotes the L ka value, right? What is L for S?
Oh, then only 1.
0.
Because 0.
It will be 1 then.
1 plus 0 is 1. Yes. I'll just write this whole thing in an order over here. यहाँ तक ठीक है. All right. Similarly, 2s में n plus L value क्या होगा?
2.
Oh,
2 plus 0, 2.
oh, sorry.
P,
sorry.
n plus L
Three.
will 3. 3s n plus L will be
3,
3.
3p,
4,
4,
4.
3d,
5,
5,
5,
4s,
4,
4.
4,
4p,
5.
5.
5.
and it'll keep continuing, but let's put a stop till here. Okay. Abhi, these are the energy values as given by n plus L, right? Electrons prefer going into the smallest one first. So in sub mein se, where will the electron first go?
1s.
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 Yes, so this would be the electronic configuration ka order. So first it goes into 1s. Iske baad
2s.
2s.
2s,
2s. Iske baad
2p.
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 so 1 ho gaya, 2 ho gaya. Uske baad the smallest value is 3, which you find for 2p and 3s. So dono mein se
take it
which
for
one will it go? How do you decide?
the smaller one. That's 2p.
So n plus L is the same thing. So yes,
No, the n ka value which is smaller.
correct. So the primary energy level decider is n. So when you have equal n plus L, then look at the individual n values. So whichever is smaller, that will have a lower energy. Okay. So based on that, 2s के बाद क्या आना चाहिए? 2p or 3s?
2p.
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 2p के बाद 3s naturally does the same.
Yes.
Then 3s के बाद क्या आएगा?
3p.
3p.
Again, you run into these two, both having 4, but again, n value is lower in the case of 3p, so you get 3p. अभी 3p के बाद क्या आना चाहिए?
4s.
4s.
You see that now 3d has a higher n plus L value, which means it has a higher energy compared to the 4s orbital. That is the reason 3p के बाद 4s gets filled up and then 3d gets filled up. Okay. So 4 के बाद 5. 5 के लिए you have 2 options, 3 options in fact. 4d, 4f के बाद you get 5s also. But out of that, smallest n value is 3d. So that's why after 4s you get 3d and then you get 4p and then 5s and it continues. Okay. So this is the order of electronic configuration. And okay, so note it down and then I'll.
And the energy level n plus L can only be used for relative comparisons, right? Not just individually, we can't just say
Yeah.
Nth Shell is the energy.
Yeah, this is again, all of these are dimensionless quantities, they're just numbers. So only for relative comparison of which is higher, which is lower, that's the only reason you use this. Actual energy values are given by your Bohr's expression for hydrogen atom. For example. Okay. So Rishit, to answer your question, like obviously real life application in the sense, in your day-to-day work, you're obviously not going to cite the electronic configuration. You're not going to talk about SPDF orbitals, but knowing this is important because from this, like the more you use this in your 11th, 12th, and then your undergraduate, you start building an intuition, which will tie into, like the higher level operations and the knowledge that you use. So these are basically your fundamentals. The way you learn addition, subtraction, multiplication in math. Yeah, that's the reason you didn't have to know everything about Schrodinger's wave equation, but you needed to know the equation to know the fact that, oh, that's where your NLM is coming from. And the reason why you need to know NLM is because that's where your SPDF is coming from. So that is the reason why you have to go through all this. Okay. 2-3 people are done. So Sanat, Rishit, Ritu, let me know when you guys are done.
Oh yeah, I'm done. I just forgot to tell.
Ritu?
Me too, I'm done.
Okay. All right. So now this should answer your question, Ritu. So you can see that 1s occupies, you get your 2 electrons here. From 2s and 2p, you have 2 plus 6, 8 electrons. Then 3s and 3p, the third orbital takes 2 plus 6, 8 electrons. And that's where you're getting your 2, 8, 8, 2 from. And then you jump to the fourth, and then you come back to the third orbital after that.
Doesn't it become like 2, 8, 18, 8?
2, 8,
18, 8.
If you're looking at atomic numbers beyond like 50 and all, yes, it becomes 2, 8, 18, 8. But when you look at potassium, calcium and all, in the third orbital, you're just filling up the 3s and 3p. You're not touching the d orbital there. That is why you have 2, 8, 8, and then 1 or 2. Here. Now, for every single element, it's difficult to remember this order, right? Like if you have to memorize it. And honestly, do you really prefer memorizing everything? Or would you rather have like an easy shortcut way to figure it out?
Shortcut.
No.
Definitely shortcut.
Easy to have a shortcut, right? So that is the reason you use something called Morse diagram or Morse figure or something like that. I don't know his name. You don't really use his name so much, but his logic, you use it every time. So the easy way of remembering this order, so you write down the electronic configuration in this format. So each orbital you kind of make like a half a pyramid kind of structure. You put all S in one line, all P in one line, all D in one line. Then you draw a line diagonally. Okay, start from top right and your direction should be in bottom left. Top right to bottom left, what is the first orbital you're going to encounter?
1s.
1s. Khatam ho gaya. Then again top right to bottom left, then which one are you going to encounter?
2s.
2s. So 1s ke baad 2s aaya. Then 2s ke baad which one are you going to encounter?
2p and 3s.
2p3.
Yes.
Uske baad 3s. And then s ke baad khatam ho gaya. Then 3s ke baad what will you strike first?
3p and 4s.
3p,
3p.
4s.
उसके बाद 4s. Then 4s के बाद
3d, 4p, 5s.
3d, then 4p, then 5s, then 5s के बाद 4d, then 5p, then 6s, and then 4f, then 5d, then 6p, then 7s. So that's how Morse diagram helps. Like you don't have to keep calculating n plus l and then, you know, figuring out the order. Like you don't have to do all of that. You just draw, you write the orbital names in this particular way, just line up all the S and P and D and F. And then start from top right, diagonally draw an arrow, and that will give you the order of your orbitals when, like order of the electronic configuration, straightforward. 3p ke baad 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, 5d, 6p, and so on.
Ma'am, I had a doubt, so maybe I forgot. But how is 2p 6? Like 6 electrons?
How many orbitals does p have?
How many orbitals?
Huh.
I guess 3.
3 orbitals, right? And each orbital can take how many electrons total?
I guess, yeah, then 2 into 3, okay.
Okay. So using this, you can build the electronic configuration of any element in the periodic table. In fact, after this, either after chemical bonding or before chemical bonding, you have a chapter on the periodic table. And if you have the periodic table in front of you, you don't even have to do all of this. Just looking at the table, you can figure out the electronic configuration. And that's exactly what the periodic table should do. You shouldn't remember the periodic table, you should use it to figure out the properties and configuration and all that stuff.
How can we use it to get like 2s, 2p and those all?
So once you're done like writing this, I'll just show it to you. Periodic table is honestly like a magic thing. It's so important. So fun. Okay, but I guess clear about this notation of figuring out the electronic configuration. Yeah, you won't be asked this directly in the exam, but this is mentioned in the textbook. This is explained to you because you will be asked to write electronic configurations in the exam, and for that, this is going to help you out. It's like an easy way to figure it out. So practice this, do a bunch of electronic configurations, and you'll be perfect with this. So while writing electronic configurations, one thing you need to be careful about is knowing how many electrons each of these orbitals can take. Because there, if you make a mistake, then your configuration is going to be wrong. So you should know that S will stop at 2, then P will stop at 6, and D will stop at 10. So that part you need to be careful. Guys, again, all of you have, like, it's been almost an hour since you guys shot your videos, but keep it on. At least I'll know if you're still writing or if you're free or, you know, like whatever's going on. Okay, Arnab said yes, Adit is done, Ritu is done. Smira, you had also reacted, right? Yes, okay. Smira and Rishabh both are done. So Kaveri and Sanat, let me know when you guys are done, yeah?
I wrote to you in the chat.
Good, okay.
But I'm done.
This whole thing,
Yeah.
this, okay. Cool. Oh, we were doing, I was to show you the periodic table, right? Okay. So this is the classic periodic table. Good resolution. Okay. How much about the periodic table do you guys remember? I think you had it in grade 10, no? Do you remember the overall blocks? There's something called the S block, P block,
S block, P block, P block.
Do you remember where do you find the S block? That part you don't remember. Okay,
I forgot.
that's fine. So the first two rows, these two are the S block. The right side, this all these 6 rows together form, or 6 columns together form the P block. This
The
rectangle,
center is the D block and the lanthanoids, actinoids are the F block.
correct. The reason why they're called S block, P block, D block, F block is because the electronic configuration of the elements, the final, the valence electron for S block goes in the S subshell. The final valence electron in P block goes in the P subshell. And for the D block, the valence electron goes in the D subshell, and then the valence electron goes in the F subshell. So if I had to figure out the electronic configuration of, say, sodium, can you guys write the electronic configuration of sodium, like in general? How many electrons does sodium have?
281, 11.
281, yes. So this is a 9 standard answer. Now give me a 11 standard answer. You can refer to
Yes.
the thing just now, like one starts with 1s1, then so sodium atomic number is 11, so it has 11 electrons. Starts with 1s. S can take how many electrons?
2.
1s2. Then 1s के बाद क्या आएगा?
2s.
2s can take 2 electrons. So 11 में से you've used up 4 electrons. Okay. Then 2s के बाद क्या है? 2p.
2p2.
2p, 2p.
How many electrons
Sorry.
can p take?
2p6.
So
P6.
6 electrons.
Total, how many electrons have we used up?
10.
And
10. So remaining there is 1 electron. So 2p के बाद that 1 electron will go into
3s2.
3s1.
It'll be
3s1.
3s1.
1.
1. So S can take 2 electrons, but sodium has only 1 remaining. So it ends with 3s1. Okay. So now coming back to the periodic table, the reference. So the key is that each row, so that each period is representative of your n value, and each group is representative of like the number of electrons. Okay. So the first period has only 2 elements, so that's 1s1 and 1s2. And the second one, S block may there are 2 elements, so this is 2s2. P may there are 6 elements, so this represents 2p6. And then we land at sodium, that is why this is 3s1. Similarly, I can just looking at the periodic table, I can tell you the electronic configuration of, you guys choose an element. Actually, let's
Whatever
play a game.
this,
You guys choose an element and you can Google search and have the configuration in front of you, and then you can check
Hydrogen.
whether I'm right or not.
Thorium, 90.
Which one? Thorium. Okay. Do you have the electronic configuration? Okay. So Ritu said thorium. Where is thorium?
90.
F block. Okay. 90. Okay. So thorium will be 1s2, 2s2, 2p6.
90 would be too long, right? Like we keep on doing.
3s2, then 3p6, 4s2, then 3d10, then 4p6, 5s2, then 4d, 3d के बाद 4d आएगा. Thorium comes after here, so I'm still safe. 4d10, then 5p6, I've reached here, 5p6, then 6s2, then 5d10. So before 5d, then I get 4f14, the 14 elements here. So I suppose, I think I get 4f14 first and then 5d. 4f14, then 5d10, and then 6p6, then 7s2, and 5f1 or 2. Let's see. Till here is 30, 36, 32.
Just a 7s2.
7s2 will be radium. You said thorium, right? So 2 more electrons. I think it would be 5f2.
The Google one only says like 6d2 and 7s2.
6d2 and 7f2. 6d कैसे आएगा?
I don't know. I Googled it. It's the first thing that popped up.
Maybe it is
Yeah, that's what I'm
represented
getting on
as
Wikipedia.
Rn. Does it say like?
Yes, ma'am. It's showing. Yes, ma'am.
It shows Rn, and then the s electrons will be there. 7s2, and then yeah, and then the f electrons will be represented.
Yeah.
So that is like a short form representation of the electronic configuration. But yeah, this is how you use the periodic table to figure out the electronic configuration like easily enough. So that is why the periodic table is designed in this way. It's designed to make it easier for you to read, to figure out what an element is like. So looking at the position, you should be able to get what family it is in. Based on that, you get the valency, you get the where the valence electrons are there, and all these things. But we'll get into the detail of it in.
What does the Rn mean? Does it refer to like 86?
Yes. So Rn represents radon. So yeah, like we'll we'll practice writing the periodic table, and then I'll tell you what are the short forms, like, you know, why do we put it in square brackets and all of that. Okay. Cool. So now you guys know the order of filling up the electrons. Now we go one step deeper. So you have Pauli's exclusion principle. So according to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. Remember what I said about the address? Like, you can't have 2 electrons occupying the same thing. So the set of 4 quantum numbers that you have, each electron will have a different set of quantum numbers, even if their n, l, m values are the same. Like, for example, if you take 1s, or let's go with a different thing. Carbon, you guys familiar with carbon? What would be the electronic configuration for carbon?
One S2,
1s2,
then 2s2,
Yes.
then 2p.
2p2.
P2.
6 electrons.
That's all.
That's it. Okay. So 1s2 is occupied by both the electrons first, and then you have 2s2, and then you have the 2p electrons being occupied here. So if I consider, let's say, one of the 2s electrons, or consider both the 2s electrons. Okay. So if you focus on the 2s electrons, what are the 4 quantum numbers that the 2s electrons would have? Quantum numbers, matlab, write down the n, l, and m values for it.
N will be 2.
N will be 2 क्योंकि 2s का है. L will
L
be,
will be 0.
yes, s orbital है, so L will be 0.
M also 0.
M will be 0. But there are 2 electrons, right? So they both will differ in their s value. So one electron will have s as plus half, and the other electron will have s as minus half. Yeah. So that way, if you write down the n, l, m, and s values for every single electron, all of them will have a completely different set of quantum numbers. Yeah. So any 3 values might be the same, but the 4th one will always be different. So for example, if you
the
compare,
spin number will always be different.
so it depends. If I compare a 1s electron with a 2s electron, दोनों का L will be 0, दोनों का M also will be 0. And if I look at the first electron, both of them will have spin plus half only, but the N value is different. 1s में N is 1 and 2s में N is 2. And similarly, if I compare a 2s and a 2p, N is same, M may be same because P maybe you have minus 1, 0, plus 1. So P also, L, N is same, M is same, but L values will be different for both. So that way, 4 quantum numbers, no 2 electrons in an atom can have the same set of 4 quantum numbers. At least one will be different. They may have different N, they may have different L, they may have different M, they may have different S. Any one will definitely be different.
What's the point in saying this? Because S तो हमेशा ही different होगा.
हमेशा नहीं different होगा ना कावेरी. I just gave an example.
I didn't understand what you said.
Same carbon atom का. Let me just clean it up. Okay, if you take electrons in the same orbital, S values will be different. Now compare the quantum number of a 1s electron and a 2s electron. So 1s में what will be the N?
1.
1.
2s में?
2.
What will be L?
0.
0.
N into S?
1.
Huh?
Sorry, 0, 0.
0. And M?
0.
और इसमें? And S? I'm considering the spin up electron in both. इसमें
Plus half.
1 by 2, 1.
and plus half, right? So in this case, your S values are the same, but
Yeah.
N values are different.
So in this case, we're comparing 2 electrons in the same direction but of different orbitals. So anyway, so one thing has to be different.
Yes.
And if we're comparing of the same orbital, then S has to be different anyway.
Correct, yeah. So it depends on which 2 electrons you're comparing, but at least one of them is always going to be different. So that is to say, no 2 electrons can have the same set of 4 quantum numbers. At least one value should be different. It may be different in like all 4 values also, who knows, but at least one should be different.
Do we have to note this down, this principle?
Yeah, Pauli exclusion principle is important. Note down the statement. The significance of this, they cannot have the same set of 4 quantum numbers, implies that 2 electrons cannot occupy the same orbital and have the same spin. Okay, Sanat is done, Smira is done, Adit is done, Arnav, yes, done. Rishit and Ritu is done, Rishit is done. Okay, cool. So that's Pauli's exclusion principle. So yeah, it's just giving examples. Only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. So this is a case of when their NLM is equal and S should be opposite. So both having the same spin is wrong. They should have opposite spin because their quantum number should be different. Okay. Now this is important. Hertz's rule of maximum multiplicity. Okay. So Hertz's rule says that pairing of electrons in the orbitals belonging to the same subshell, it does not take place until each orbital belonging to the subshell has got 1 electron each. That is, if it is singly occupied. So pairing will start taking place only when it's completely filled up. Okay, you guys want to note it down now, or should I explain it and then you'll note it down?
You explain it, then we'll note it down.
Okay. Okay. So what Hertz's rule is saying is that let's take the case of nitrogen. What is the atomic number of nitrogen?
7.
7.
So what should the electronic configuration be?
2,
1s2,
1s2.
2s2,
2s2.
Yeah.
2p6,
6, but nitrogen doesn't have so many electrons. इसके साथ ही है. You filled up 4 of them, so remaining will be
3.
So you have 2p3. Okay, so if you look at the orbital diagram for this, 1 is a single orbital, so that will be filled up first. Both the electrons will go in. 2s is also a single orbital. Both the electrons will go in. Now coming to the p orbital. P has 3 orbitals. How can you, or how should you arrange the 3 electrons in these 3 p orbitals?
So first,
One in each.
Yeah. So what Hund's rule is saying is that you need to, like, the 3 electrons have to, like, all the orbitals should be singly occupied first before they get paired up. So the 3 electrons, each of them will want to be in its own orbital. If you're adding a 4th electron, then pairing will take place.
ma'am, in this case, you've drawn the full arrow. So let's say it's 4 and the 4th one will be occupied along with in the first box. So if you do 4,
It is 4, then it's going to be like this.
that will be half. Yeah. But the remaining 2 will be half.
It's just sake of representation. I'm sure you will come across some prints where they denote it with full arrows also. It's just stylization. But yeah, so the second case, like this case, will not take place. So each needs to be singly occupied first, only then pairing can take place. Pairing will not happen right off the bat. Okay, so imagine, there's 7 of you here, excluding me, and let's say you were going to occupy rooms in a hostel or something. Would you prefer having a single room to yourself, or would you prefer sharing?
Single room.
Single
You
room.
prefer staying on your own, right? So think of that for electrons also. They would much rather, have the whole orbital to themselves, and only when there is no vacancy, then they start pairing up. Okay. That is Hund's rule of maximum multiplicity. Yeah. So I'll just do this. You guys can note down the statement. Yeah. So it's a whole statement. It's given us 2 points because easier to read that way. The pairing of electrons belonging to the same subshell, like all the s electrons or the p electrons. The pairing does not take place until each orbital has got 1 electron each. So until it is half filled, it won't start pairing.
Does it have to be like plus half filled first, or can like the negatives be filled first?
That's the convention. We go with upward spin first, and then you start doing the opposite.
It just has to be in the same direction. All 3 that we fill first. All of that we fill first, right?
Yeah. The convention is that you usually go with, like, you show the upward facing arrow. That's the convention. Again, these are electrons. It's not like you can see them going in a certain direction. And then, like clockwise, counterclockwise, like what I see as clockwise would be counterclockwise for you from the opposite direction. So don't go by, this is how it is. This is the convention. You show upward facing arrows first and then the downward.
Ma'am,
Yeah.
just P, D, or F. Why not S?
Yeah, because S has only 1, right? Like it's going to pair up. There is no question of it being half filled. That's why. PDF have multiple orbitals. That's where this this question comes into picture, like the situation.
Ma'am, will we have like theory questions asking to like state these rules and principles and all?
Yeah, just the statements. That's the reason I'm asking you guys to write this. Just the statement.
With this, the chapter is done.
Basically, I mean, we still have to practice writing electronic configurations and look at application-based questions based on this. But as far as theory goes, it's basically done.
Electronic configuration is not part of theory.
No, it's not theory. Yeah, it's application of like all of this stuff.
Do we have a Quizlet for like grade 11?
No, there's very limited topics I can think of that we can put in Quizlet. Like organic chemistry may, for the nomenclature bit, there are a couple of sets that I had made. Beyond that, not sure. BSc PR, like for the next chapter, chemical bonding may, there's like a little bit that I need to remember. There's a few sets here and there, but like not particularly for the whole thing. Again, I told you, right, like this year, it's going to be completely understanding or application based. You'll have very less stuff to memorize. And even if you're expected to memorize some things, it's not like you're not going to be asked a direct question on it. Like you don't have to reproduce it word by word. You just need to remember those terms so that you can use them in your answers. Oh, Ritu, you had sent a question. I just saw it. This is why
I figured that out when you answered the previous one. Read it out.
Electropositive up to 3. Again, that's completely based on the energies only. And yes, because even for the d electrons, you have +2 taking place after it's going into the p thing. Yeah. Okay. So now rest of the part is like figuring out the electronic configuration for every single element. So for hydrogen, there's only one electron, so that 1s electron goes in the 1s orbital. Helium, 2 electrons, so its electronic configuration is 1s2. Both the electrons goes in the first box only. Then subsequently, you've got lithium, atomic number 3. So the 3 electron go in 2 in 1s, so 1s2 and 2s1. Subsequently, you have beryllium, 1s2, 2s2. Boron, 1s2, 2s2, and 2p1, and you can start building it. So at nitrogen, you can see that the next, like carbon and nitrogen, the electron goes in the next orbital. And at oxygen, you can see that the 4th electron pairing takes place after all 3 are filled up. This is the electronic configuration. Yeah, Ritu?
In like helium, we saw like the 2s, like there were like both the arrows, and like even neon, like they're all up and down the field. So why isn't beryllium like the same way? Because it follows like the trend of the inert gases.
What?
Like in neon, like the arrows, like all the boxes are filled.
Yeah.
Even the helium, the same thing happens. How come beryllium isn't like inert then?
Inert, because it's only the 2s that is filled. So in neon, 2s and 2p, like whatever 2s, 2p, the whole of the second orbital is filled. But for beryllium, only 2s is filled, its 2p is still empty. So Another thing is, again, this we'll study more about it in when we do chemical bonding. So for stability, you need an octet configuration. It was found out that octet is the most stable configuration. So you need to have octet, means again oct, so that's 8 electrons in the outermost shell. So outermost shell of beryllium is 2s. So it needs to have 2s and 2p filled for it to be stable, but it only has 2s filled up, like its 2p is completely empty, which is why it does undergo chemical reactions. So that is the difference between neon and beryllium. And for helium, its 1s is completely filled up. Yeah, it doesn't have octet, but I mean, 1s, it doesn't have the capability of accommodating any more electrons also, right? Like whatever is the maximum possible is filled up. That's why that's not good. Okay. So similarly, you've got, oh yeah, this is another thing. So talking about stability, energy values and all. So usually symmetry is usually denoted with more stability. Like if you come across symmetry in nature, be it in electronic configuration or alignment, orientation of any sort of orbitals, bonds, symmetry equals stability. Okay, so that way the completely filled up shells and half filled shells are basically more stable than incompletely filled shells. Okay.
Ma'am, but half-filled shells would be incomplete only, right?
Half filled means exactly half filled, like in the case of nitrogen, where all the orbitals are occupied by 1 electron each.
They are what? I couldn't hear you.
So half filled configuration, like you have for nitrogen, and completely filled configuration, like you have for neon, are considered to be stable. Here. So similarly, if you come across a configuration where the valence shell 3D, like D can take a total of 10 electrons, but a configuration of 3D 5, because all the orbitals of D orbit, like D subshell, are half filled, exactly half filled. So this would be a stable configuration. So this gives rise to some anomalies later on. So, but the point, like the logic, the point is that completely filled and half filled subshells are stable. And why are they stable? Reasons are given. So one is the symmetry, the symmetrical distribution of electrons. So symmetry leads to stability. I was just mentioning that. So completely filled or half filled subshells have symmetrical distribution, like equal uniform distribution, and that's why they are more stable. And another one is exchange energy. Okay, what is exchange energy? Okay. So the stabilizing effect arises whenever 2 or more electrons with the same spin are present in the degenerate orbitals of a subshell. Okay. So this we'll have to go a little more deeper into the subject. So in P orbital, this doesn't coming to like it's not very significant in the P orbitals, but this is more significant in the D orbitals. Okay. Do you guys remember what the 5 orbitals of D are? So D has 5 orbitals, right? M values range.
EXY. Oh, okay.
Yes.
Y,
DXY.
XZ, DYZ,
Yes.
DZ square.
and
DX square, Y square.
Finish off the symmetry. XY, YZ, XZ. And then
X square, Y square.
X square, Y square, and
And
Z
then
square.
Z square.
dz square. Yeah. Okay. So within the d orbitals, these three tend to have like again, these three are oriented differently from these two, right? Like d x y y z and x z are basically oriented between the axis, and d x square y square and d z square are oriented like along the axis. Z square is like along the z axis, x square y square is like along the x and y axis, right? So depending on the situation, like when the element is existing on its own, is like perfectly fine. Like all of them are equal in energy, equivalent in energy, no issues at all. But when it's approached by an anion, where is that anion approaching from? Like, is it approaching from equally from all sides, or is it like approaching only from four sides along the axis? Like that tends to affect the orbitals. Like that we'll get into it deeper when we study about the D group compounds, about coordinate compounds. But yeah. So yeah, like when the orbitals are equal in energy, so those orbitals are called degenerate orbitals. So when the orbitals have equivalent energy, they are called degenerate orbitals. Okay. And electrons, they have a tendency, like because they're interacting with light and they have all this energy, like they are constantly moving, right? So they have a tendency to basically like jump across orbitals of equal energy. Okay. So these electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. So the number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. Okay. So if the electrons, if the orbitals are not half filled, right? Like if there's like empty orbitals and there's a single electron and the rest of it is empty, then like there's no exchange as such. Like this electron can jump in, like it absorbs energy, jumps in, and then releases energy, comes back to its position. But when all the orbitals are filled, like when all the orbitals have at least one electron, like when the situation is that it is either half filled or completely filled, the total energy that is released when the exchanges take place, so that exchange energy is maximum. So that leads to the like that contributes to extra stability. Okay. So basically, yeah, bottom line is that half filled orbitals and completely filled orbitals means stability. Now that is important because whenever the atom has a chance to, just with one minor change, if it can get that extra stability, it is going to get that stability. Okay. Like for example, what is the atomic number of chromium? Like you can Google it. Like I don't expect you guys to know it. You can Google, check it out, find out.
24.
24.
24. Okay. Now figure out the electronic configuration. Now this you don't Google, like tell me, like build the electronic configuration. Starting to आसान है. Always starts with 1s2, then 2s2, 2p6. उसके बाद क्या आएगा?
3s2,
3s2, then
3p6,
pp6, then so 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18.
4s2,
So 24 में से 18 electrons हो गया. 3p के बाद correct, very good, 4s2.
4s2.
Then after that
3d4,
3d4. Okay. 3p6 tak ignore it. This is like noble gas configuration. Now focus on this part. So you have 4s2 and then you have 3d4. Two, 3, and 4. Okay. If you were to make this whole thing symmetrical, like if you want to make it uniform, what can you do?
take one electron from 4s2
S
and put it in 3d4.
Correct. So the natural configuration of chromium, like if you do the spectroscopic studies and if you figure out the configuration of chromium, that's what it does. Like theoretically, the order says this, but because half filled is more stable, like completely half filled is more stable than partially filled this thing, its configuration changes to 4s1 3d5. So this is what chromium does. This is the natural configuration of chromium. This is the actual electronic configuration of chromium. Okay. So there are certain exceptions because of the
Ma'am,
stability. Yeah,
so in the exam, which way do we write it? Like the first or the second?
this one.
Okay.
This is what you would expect, but because half filled is more stable, turns out chromium's actual electronic configuration is this.
So technically both are correct.
No, this is the correct configuration. This is what you'd expect, but because of more stability, this is what chromium's configuration actually is.
Well, we have to remember like the noble gas configuration so we can see how much more to balance it out from.
Up to you. Like if you want, you can remember it and you can write like the short form of it. But I don't know if your school is going to accept it or not. Like better check it with your teacher if you can do that.
So like just remember the last digit, like just in case, so we know like after that you have to balance it out.
Yeah, like you need to know the atomic number of that particular noble gas. Like in this case, 18 belongs to what? Neon ke baad argon. So you need to know that correctly. If you write krypton by mistake, it's going to be wrong. That. No, but what I mean is that I don't like if you present your answer like chromium ka configuration as AR4s1 3d5, I don't know if your school teacher is going to accept it or not. So just check it.
Ma'am, hello.
Huh?
I got disconnected when you was explaining this one. Could you please briefly explain it again?
At what point did you get disconnected?
You were writing the configuration of chromium. No, chromium name.
Oh, nothing simple. Like half filled is more stable, right? So what chromium does it instead of 4s2 3d4 makes its configuration uniform by shifting one of the 4s electron to the 3d orbital. So its actual correct configuration is 4s1 3d5. And the reason why it favors this configuration is because half filled orbitals contribute to more stability.
If it's 4s1 3d5, then it's half filled.
Yeah, because 3D has 5 orbitals and each of them is occupied by 1 electron each, half-filled configuration.
So just the last one we talked about.
Huh?
Only the last one we're seeing, 3D5, only the last
Yeah,
shell lot.
yeah. And the reason it does this is because, you know, it just needs 1 electron to complete this half-filled configuration. So it's just going to spare 1 electron from 4s, put it to 3D. Yeah. So similarly, you will observe this again in the case of copper. So if you see copper electronic configuration is 29. 3s to 3p 6 तक ठीक है. So 29 matlab you would expect, like according to your calculation, you'll end up with 4s to 3d 9. But instead of 9, 3d 10 would mean that the third subshell would be completely filled up. So it favors that, you know, even though 3d has more energy than 4s, the extra stability is worth it. It brings down the overall energy down. So the actual configuration is 4s1, 3d10. Yeah. So any place that you encounter these kind of anomalous configuration where it is differing from what you'd expected, like based on what the rules are given, it's because there is always a reason for it. So in this case, in chromium's case, it's half-filled orbitals being extra stable. And in copper's case, it's like fully filled orbitals being extra stable. Basically, extra stability is the reason. And of course, like this pattern would be followed in the higher elements also, like just before copper, whatever is there. Just below chromium, whatever is there on that.
So if it's 3D10, then what?
If it's,
If the last one is 3D10, then what?
how many orbitals does D have, Kaveri?
Sorry?
How many orbitals does D have?
4, yeah, 5, no, 5.
5, right? So if there are 10 electrons, basically all the orbitals of this D are completely filled.
Yeah.
Yeah, so that leads to extra stability. Like again, we discussed earlier, right? Fully filled orbitals are more stable than partially filled ones. So either
So
half,
if it was 3D9, then?
if it was 3d9, you tell me, like if there's 1 electron missing, if it was 3d9, is that filled?
So the last one would be only half filled.
Yeah, this is empty, right? This is like incomplete, it's partial, and it's not even symmetrical. So for extra stability, it fills up this, takes 1 electron from 4s and fills up the d orbital.
Okay, so if
So
we
it's
see
okay if 4s is incomplete.
4s is incomplete, or you can say 4s is half filled. Yeah.
So if we see an exception like that, it means that it's looking like for stability and it's not complete in the other way.
Yes. So if there's any anomalies, exceptions, there is always a reason for it. More often than not, the reason is stability. In this case, yeah, half-filled configuration and fully filled configuration leads to stability, which is why it does that. And this is evident, like you can see that copper shows valency of +1 and sometimes +2. But any of the other D block metals don't, like iron doesn't, manganese doesn't, nickel doesn't. Chromium, again, there are places where it shows +1 valency, oxidation state. All comes down to the electronic configuration. Like those are the applications for sure. Why is this forming so and so high? Yeah. That is the end of the chapter, you guys. The main part of like whatever we discussed today would be knowing the rules, like the statement of the rules, the fact that it's filled in increasing order of the energy, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. So you use these particular rules to write down the electronic configuration. Special notes on the electronic configuration is the fact that fully filled and half filled configurations are more stable. So that shows up in some anomalous configurations. Otherwise, the rule is like pretty straightforward. You just fill it up that way. Okay. Okay. So I'll